Okay. Hi, everyone. I hope all of you guys can hear me. If you guys can hear me, maybe some of you guys just give me a thumbs up so I know that you can hear me and you can see the screen as well. Okay. Thank you, Gabby. Thank you, Lloyd. Now, for today, right, I believe most of you guys signed up for the WA1 revision on both your general wave properties as well as light topic for set 4 because I believed based on what my regular students do tell me is that you will be having your WA1 soon. So hopefully this session can help you guys better in your WA1 topics and hopefully you guys can get whatever grades that you want. Okay. So let me just do a very short introduction about myself as well as the center so that those of you guys who are not overmarked students or who are not overmarked students actually know what we do here and who am I. Okay, so you will not be wondering who is this stranger teaching you for the next 1.5 hour. I'm Miss Pamela and I have been the O level and A level physics tutor in at Overmark for the day since they started, but I've been teaching for at least 14 years ever since I graduated from university. So I do have a master's in education, trying to figure out how you guys do study as well as how you guys learn. And if I can, try to mix in a little bit of technology into your education studies so that it is not so boring and maybe tap into how technology can help you guys learn better in the future, but that's just a side project of mine. So I have classes currently running in 2026 as well as a student batch of about 80 students a year. And I mainly teach at Tampines and Kovan because that's where I stay near at. I stay near Tampines and these two locations are nearer to where I stay. Okay, so that's the tutor side of me. Now, the real me or not saying the real me, but the side of me that is out when I'm not teaching is that I'm a mom to not a new mom to a baby boy. His name is Atlas, and I'm very proud of him. He's my pride and joy. As well as for me, right? My hobbies are I love Formula One. I love Taylor Swift. So any of you guys who are fans of these, right? You can come and speak to me about it. We can have like a tea session about these two. Okay. Now, another fun fact about me is I do learn a little bit of French, and it's something that is ongoing as well. So I hope that uh, any of you guys who have hobbies and interests that aligns with me or can match me, we can hopefully vibe together. Okay, so a little bit about Overmark for those who are not yet our students or this is the first time you are hearing about Overmark is that we are sort of like a Gen Z tuition center, mainly because our tutor pools are kind of young. And we do that is because we try not to have a huge age gap with you guys so that hopefully at the end of the day, if you have any issues or problems, right, we are still relatable. We can still speak to each other about it. And for this page wise, we do have several branches across Singapore, not because we want to flaunt our branches, but more of we want to show you guys that if you do sign up with us as an Overmark student, you get to have access in any of the centers to study, to chill out, to basically have somewhere you want to rest or whatnot if you're waiting in between tuitions. And most of my students do use the centers as their studying place because nearing the exam, I know some of you guys, most of you guys actually do studies outside, at Starbucks or the airport or the library, and it's very hard to get seats. So our centers are basically available to the students for a study session when you are nearing your exams. Okay. Now, our results wise, I wouldn't want to boast that these results is for Overmark, but it's more for the students themselves because I always believe that when my students come for Overmark's lesson, the results that they get at the end of the day is purely 70% the student's effort, 30% my effort or the Overmark's tutor's effort. Mainly because, right, it takes two hands to clap. It is not possible for me to help you get A without your effort, and it's also not possible for you to get an A without me helping you to facilitate. So most of the students, right, they would come and tell me, say, "Oh, Miss Low, I want to have B in my result, or I just want to have pass, or I just want to have A." My job is very simple. It's just to facilitate you from day one until doomsday. Okay, so that at the end of the day, you can see that our effort together help you to achieve whatever you want to achieve at the end of the entire year. Okay, so that's what we usually do. Our promise to you and our vision as well for most of the students here. Okay. Now, being an overmarked student, you get to also have a few resources. Now, the resources that you receive today will be a sneak peek of what are the resources that you do receive at an overmarked session or an overmarked class. The curator notes is for sure. The exams questions as well as the weekly worksheets are for sure as well. And what we have additional that makes us very different from other centers are we do have practical hands-on experiments, our curated practical notes, as well as our mock exams. Now, all of these are not to actually scare you or pressurize you, but it's more of to give you an additional exam condition so that when you go to the exam, it simply just becomes another session. So you don't have receive a culture shock, or you don't have like, oh, this is the first time I'm in this situation. So what we try to do is we try to recreate exam conditions as much as possible so that you are not so taken aback by the kind of things that can pop up during an exam. Obviously, we do try to do some spotting or do what are the scenarios that can come up that can jeopardize your exam condition. We do try to come up with those kind of scenarios outside of the exam hall so that you are well prepared for them as well. And on top of that, we do have cheat sheets as well as after class consultation for the students. Okay, so this is really a very brief and fast introduction of Overmark, mainly because I want to go into the details of the WA1 revision so that hopefully all of you guys at the end of this lesson will be more prepared for your WA1. Now, for those of my students who are regular students, um, they are very used to me in class. Hello, Leroy. Okay. And hopefully today's session will be an additional session for you guys so that you are better prepared for WA, and I expect you guys to get I don't expect you guys to get A. No expectation here, okay? But I expect you guys to do your best so that at the end of the day, you're happy with the results that you get. Okay? Now, before I start the session, for those of you guys who do not yet have the worksheet or you have not yet downloaded the worksheet, I have sent it into the group chat. So if you can, just quickly download it and then retrieve the worksheet so that we can go through the lesson today. Okay, so I just gave all of those who do not have the worksheet yet just a minute to download it. I don't know if you guys can see, but I have a very blurred Christmas tree at the back because I have not yet taken down my Christmas tree decorations. But I changed it to Chinese New Year's decoration. Vera, I have sent it into the meeting chat on the Zoom chat. So you go to the Everyone tab and then you see if you can see it. Can you see it, Vera? Okay. Let me resend it into the Zoom chat. I think those who came a little later did not manage to see the one that I previously shared. Give me a while. Okay, I've just sent it into the group chat already. Okay, good. So let's begin today's lesson. Begins today's lesson with regards to your WA1 revision. I'm going through two topics, which is number one, general wave properties as well as light. Now, the way I'm going to do this revision is I'm not going to go through most of the content because I believe the contents, right? I placed it inside the worksheet, but it's mainly for you guys to go back and read as well as to note what are the important stuff and what are the not so important stuff. But what I'm more interested in are the questions themselves because knowing to apply the formulas in the questions is more important than memorizing the content. I repeat, in physics, we don't usually memorize content because it's like math. In order for you to do well for physics, if you just have the formulas and not being able to apply them, you will not be able to do well in the exam. So I rather you pay attention to how do you apply all of this content in your questions rather than knowing the formula very well, but yet don't know how to use them. Okay. But along the way, I will still plug in a little bit of those content so that you guys know which are the concepts to use for the different questions. Okay. But anyways, let's go straight to the question first. Now, for the first question here, it says, which of the following statement about a transverse wave is not true? Before we go on, let me just very quickly recap a little bit about waves. Okay, so you can write it in the middle here if you want. In your entire waves topic, at the end of the day, what we are interested to know is two things. Number one, what are waves made up of? And there are two types of waves in under your syllabus. The first wave, which is the longitudinal wave, and the second type of waves is your transverse wave. Now, for longitudinal wave, just take note. At the end of the day, what we are interested to know is the difference between these two types of waves. And the first difference that they have is for longitudinal waves, the particles oscillate parallel with respect to the wave motion. Take note, it is particle that is parallel to wave and not particle parallel to particle. What a lot of students tend to be confused about is they will write that a longitudinal waves is where the particle is parallel to the particle or the wave parallel to wave. If you think about it, how can a wave be parallel to another wave? So for longitudinal, it is how your particle oscillates and parallel with respect to the wave. Whereas for transverse, this is where the particles oscillates perpendicular to the direction of wave motion. So in that case here, you have a particle that oscillates up and down, okay, or perpendicular to your direction of motion. If let's say your direction of wave motion is in this direction and your direction of wave motion is in this direction. Okay. The next difference between longitudinal and transverse wave is for longitudinal, they would usually have a series of compressions as well as rarefactions. Okay. So compressions are basically region where your longitudinal waves are considered to be having an air pressure higher than that of atmospheric pressure, and rarefactions are regions whereby the pressure is slightly lower than your air pressure. So it is the difference in air pressure that creates the series of longitudinal wave that you experience. Okay. So one example of longitudinal wave, which is technically the only example in your syllabus, are sound waves. Whereas for transverse wave, there are series of crest and trough. Okay, so these are regions whereby you have the maximum amplitude for crest and minimum amplitude for trough. So a few examples in your syllabus that lies under transverse wave are things like water waves, okay, light waves, which is why you do study the topic on light, as well as EM waves, which is why you also study the topic on EM waves. Yeah? Okay, so with this summary, let's take a look at the first MCQ. Now, don't worry about copying the answer because I'll go through every question. At the end of the day, you will still get to have the answer. Now, for the first question here, it states, which of the following statements about a transverse wave is not true? Now, for this part here, they are looking for the one that is false. So let's go through all the different examples. Number one, the points on the transverse wave do not move in the direction of the wave motion. So points on the transverse wave do not move in the direction of the wave motion. This is technically true because when you talk about points on the transverse wave, basically your particle particles of a transverse wave, if you remember, moves perpendicular to the direction of your wave motion. So therefore, not move in the direction of the wave motion is correct because if they do move in the direction of the wave motion, they end up being a longitudinal wave. Understand? Now for part B, an example of transverse wave is light. I've already went through that earlier on in the examples. Examples of transverse wave under your syllabus: water, light, EM waves. Okay. Part C, option C, sorry. Transverse waves always require a medium to travel. Now, the word always here is not correct because an example of transverse waves that do not require a medium are what we call EM waves. That's why C is not true. C is the answer. Okay. Now let's take a look at part D. The direction of vibration of transverse wave is perpendicular to the direction of wave motion. So when you talk about the vibration of the transverse wave, they're actually referring to the particle. So this is particle perpendicular to wave, therefore this is correct. So for question 1, C is the answer. All right, next, question 2. A Reaper tank is set up so that there is different level of water as shown. Now, if the vibrator produces a straight waves, which of the following diagram correctly shows the Reaper approaching region R? Now, if you note the difference here, you can see that this vibrator is situated in a path that is of a deep region. And then it is going to travel towards a shallow region. And then it's going to travel to shallower. And then it's going to travel to shallowest. So this wave is going to travel through different regions or from deep all the way to shallow. Now, I want you all to study this question because the concept for this question is very, very important. It is often commonly tested in your exam. And the concept would be, let's go back slightly upper to the content here. So what happens when water moves from deep water into shallow water? Okay, I need you guys to understand that water waves are your normal waves, which means they undergo properties like what the waves do. And if you recall in light, they undergo reflection and refraction. That means water waves themselves also undergo refraction. And the refraction part of water waves can be observed when they move through a deep region and to a shallower region. So if you take a look at this diagram here, these are what we call wave fronts. So basically the waves are denoted here. Now, the distance between two wave fronts are your wavelength. So what do you realize about the wavelength as your water moves from deep to shallow region? You can see that the wavelength starts to decrease. So what I usually like to write in class for my students is this. When water moves from deep to shallow region, number 1, your wavelength starts to decrease. Okay, that's not number 1, but that's the last step here. The wavelength decreases. Okay, but our job is to explain why the wavelength decreases. Okay, so the final answer here would be, okay, wavelength decreases. Now, what is going on in between to tell us that wavelength decreases? Number 1, when water moves from deep to shallow region, think of it that it is now approaching to much nearer of a seabed. So initially it was further away from the seabed. Now it's much nearer towards the seabed. So if it's closer to the floor, that means your friction between the water and the floor, seabed, will start to increase. Okay, will be right here. Friction between water and seabed increases. Okay, don't necessarily have to be seabed. It could be the floor of the container or whatnot as well, but generally it increases. As a result, these will cause it to slow down. But there is a condition for this to happen, which means the frequency of the wave needs to remain constant. Why? Because, right, frequency is something like an identity of the wave. It doesn't change unnecessarily if the question state that the frequency is changed, or the question state that the source of the wave is changed. So maybe now it's no longer a water wave. It could be a light wave. Okay. So as long as the source of the wave changes, then the frequency changes. But since water remains throughout, the frequency remains constant. And as a result, we use the formula that all waves follow, V equals to F lambda. You can see here that when friction increases, frequency remains constant, and V decreases, my wavelength would therefore decreases. Okay, or maybe I rewrite this. This is not sounding right in terms of English. Speed decreases since V equals to F lambda, wavelength decreases. Yeah, this is much better. Okay, so why would speed decreases? Mainly because I'm now closer to the seabed. There is more friction causing me to actually slow down. That's why my V decreases, hence my wavelength decreases. So this is how we explain water moving from deep to shallow. Okay, so shallow water, slower speed, SS lah. Just remember this way. All right, so what happens now you realize when you're actually looking at your question here, okay, is that when you have water waves that are coming out from the vibrator that are straight waves, because the question state they are producing straight waves, right? So let's say they are very, in a sense, arranged in this manner, like, what's the term for this? Equally spaced, okay, away from each other and widely spaced because they are considered to be in the deep region. The moment they enter into the shallow region, the wavelength starts to change. However, take note of the boundary. For this case here, the boundary is still parallel to that of my wavefront. Therefore, when it moves into the shallow region, what happens is that the wavelength of the wave decreases, becomes smaller, but it is still straight waves, like vertically straight down because of the boundary that is parallel to that of your wavefront. Okay, so if I were to draw the wave, it will look something like this. Let me just quickly. Okay, so you guys can see here that your wavefront now starts to decrease. Okay, so then, right, how does the wave starts to move, change when it travels into the shallower region? Now, when it travels into the shallower region, what happens is that your wavefront will now become even closer. That means, right, from here to here, the wavelength decreases. Now, from here to here, the wavelength decreases more. And then from here to here, the wavelength decreases even more. Understand? But if you were to look at the direction of the wave, how it travels is the wave travel in this direction like that, based on the wavefront. Then the wave travel in this direction like that, based on the wavefront. So therefore, based on how the boundary is like, the wave will travel somewhere around this region here. And then it will travel higher up like that. Okay. So now drawing the waves for the second shallow region, which is for this part here, your wave will start to bend to produce even smaller wave fronts. Even nearer, closer wave fronts, shorter wavelengths. So what happens is that they will generally bend up like that. Okay, if I can try to draw the lines. Okay, now this is an MCQ question. Obviously, in the exam, you're not expected to draw all these lines, and try not to draw all these lines to waste time. I'm just drawing for you guys to see so that you understand what I'm saying. Okay? Okay, I give up. I'll just draw this for you. Okay? So what you realize is now that your wavefront as it approaches this region, okay, will look something like that. Diagram like that. So same thing. You just got to follow through all the way in until you reach the shallowest region. Then you will realize that your wavefront will bend even more towards this side. But then the wavelength is even shorter. Okay? So that's why for this question, oops, wait. Okay, the answer is A. Now, to answer Jacob's question, why is there more friction? Because I've explained earlier on at the top part of the content, basically, there is more friction because the water is now nearer to the ground. Okay, so if you take a look at the content page, let me just quickly go, the content portion here. I've explained that because now the water waves approach the shallower region, there is more friction experienced by the water wave. So that's why there is more friction, then your speed decreases. Okay, so think about your water waves. They are made up of particles. Particles, little balls, when they are actually rolling on the seabed, they will generally create more friction. Okay. Okay, so this answer is answer A for this question. For those of you with questions, don't hesitate to ask me in the Zoom chat. Okay, now let's take a look at the next part, question 3. Question 3 is also another very popular type of questions that do come out for the exam, other than your occasional, testing for definition. And it's a concept that you need to master, which is this kind of question. They will give you sort of like a freeze frame of a certain wave, and then they will give you particles on the wave. And in this case here, they give you X, Y, Z. They also tell you where the wave is moving. The direction of the wave motion is moving towards the left side. So they ask what happens next. So for this type of question, right, your job is very straightforward. Always draw the wave after. Okay, that means what happens to the wave in the next second. There is no combined physics, J, for today. It's purely pure and IP. But if you can see in, the questions are still sort of relatable because the content are still sort of similar. It's just that your questions are easier. How do you know how steep the gradient of the wave is? SH, your question is a little bit inaccurate in the sense that wave is not a graph, so there is no gradient. Are you referring to the wavefront for question 2? How do you know it's not C? Oh, okay. Because, right, if you look at the diagram, you are moving from shallower to shallowest. And if you look at how the wave actually um rotate, you can't have C because C means, right, it is almost parallel to the boundary. So your wave cannot be parallel to the boundary unless it is a straight wave. That's why A is the only possible answer. Okay, now let's take a look at question 3. Like I said, this type of questions always comes out, and your job is you draw the wave after. So what do I mean? So let me just very quickly draw the wave here first. This is my original wave, correct? The wave after would mean based on the direction of my wave motion, my wave will move over to this side. So you got to draw the dotted wave. And then once you draw the dotted wave, you can see your particle Z actually moved upwards, your particle Y moved downwards, your particle X moved upwards. Okay? And this is because of the concept that for a transverse wave, for this kind, the particles only move up and down. They don't move left or right. Your wave can move left or right. And in this question, it moved to the left, but your particles moved up and down to create the illusion that the wave moved to the left. Okay? So what happens next in this case here? Y and Z remain stationary. That's not possible because we can see that X went up, Y went down, Z went up. So X moved down, no, X moved up. X and Y moves in different directions because based on the option here, the diagram here, X moves up, Y moves down. So the only answer you have would be X and Z will move up. Okay? All right, now remember this concept definitely will come out, especially for MCQ. Just draw your wave after, okay? Okay, the next one. Now, question 4. Question 4 is very similar to question 3, but I included question 4 is particles, particles will only go left and right. No, that's for longitudinal wave. Particles will only go up and down for transverse wave. Okay? Okay. Now, the diagram below shows a wave on a string with 3 points P, Q, R marked on the wave. The wave is moving in the direction as shown. So this is a transverse wave. Your wave direction of wave is then moved towards the right here. Jacob, the dotted wave is not drawn in the question. The dotted wave is what you have to draw, which is the wave after. So the next second, this is where the wave is traveling. Okay. I go through question 4 as an example again. It's similar to question 3. So they say, what is the state of motion of the wave particles at point PQR in a particular instant of time? Now note the question difference. This is asking you for the particles at that point in time, different from question 3 that happens next. For particles that says that happens next, I draw the wave that happens after. Then I say, oh, X went up, Z went up, Y went down. For this question here, same thing. I still draw the wave that is happening next later. Okay. And then I shift the wave over here. So this is what happens later, correct? Now, what do you realize? You realize that particle P moved up here. This is the new position for particle P. Particle Q moved down here, and particle R moved down here. Okay? So if the question were to ask you what happens next, okay? I just write here, what happens next? You're going to choose the option for P moved up, Q moved down, R moved down. Okay? But this MCQ question is not asking you what happens next. It's asking you what happened now at this point in time after they moved. So what you realize here is at this point in time after they moved, P is at the equilibrium position. Q is at a point randomly somewhere on the way. So on the way at a random point. Okay? And R is somewhere at the amplitude. So in the freeze frame, what's happening is you're going to know that your P, right, at the equilibrium position means it is not moving. Because your particles at equilibrium positions do not move. Pretty much like a pendulum. Think of it like a pendulum. If let's say I were to have at equilibrium position, my particle is stationary. Okay? Then if my particles were at amplitude position, they are ready to move downwards or upwards for a wave point of view. So that's why for this question here, the state of motion of particle P is stationary. That is correct. P and Q moving down, that is not correct because P is moving up. Q and R is moving in the same direction. This is correct if the question is asking about what happens next. But if this question is asking what happened at that particular instance. So imagine your particles are all freezed. They are not moving. So that's why anything that is remaining moving, right, is all out of the question. You understand? Okay. So it's important to know, right, for these type of questions, how to know where to draw the dotted wave. Okay, I redraw this one for you as an example. It's very straightforward. All you got to do is just look at where the direction of wave is. That means your wave is traveling here. So if now this is your original wave, your next wave will be, it's like this part of the wave, right? The starting part shifted here. So then you just shift it slightly to the left and then you just continue drawing. This is how you draw the dotted wave. Get it? So if let's say I change the question a bit, if the question states that the direction of the wave is this direction now. Okay, this is the direction of wave motion. Then how do I draw the dotted wave? Then I start from here. because the wave is moving over this side. So I will draw here. This is the starting point, right? I just shift it slightly here. Then I just continue parallel, like draw a symmetrical wave. Not symmetrical, what's the term? Draw the same shape of the wave. Then that's how your wave dotted line you draw. Okay? Okay, good. So let's move on to question 5. Now for question 5 here, the question says the diagram below shows displacement position and displacement time. Now take note, these two are graphs. A lot of students tend to see a wave like this, right? Then tell me these are waves. These are not waves, these are graphs. There's a difference between me showing you a wave and me showing you a graph. If I show you a graph, I'm telling you that this can be a transverse or a longitudinal wave. You wouldn't know unless you read the question and they hint to you whether it's a water wave or a light wave or whatever wave it is. Understand? They also stated that the velocity of the wave is 3 meters per second. Now, if the question gives you a displacement distance, displacement position graph, always remember the distance between one wave will always give you the wavelength. Okay, so information for the first graph gives you the wavelength. And if it's a displacement time graph, the distance between the wave will always give you the period. So that's the difference between the two graphs. The y-axis will always be the same. The distance from the bottom to the top or top to the bottom will always give you the amplitude for both cases here. Okay, so always remember, these are the only two types of graph that they can give you in the exam. Check your x-axis first. Wow. Okay, so knowing all of these, let's take a look at the next part. What do they want? They want you to give them what is the value of W. So what is W? If you look at the question here, W is the time here. Can you guys see that? The time taken for what? For how many waves? 1, 2, 3. So if one wave gives you one period, that means W is 3 times the period. So technically, my train of thought should be find the period first. Now, how do I do that? Remember, they stated that the speed is 3. You have V, you have lambda, you want to find period. So all waves will obey this fixed equation. V equals to F lambda. Understand? So our job is to find F first, which is V over lambda. Now, what is the speed? 3.0. What is the wavelength? The question here gave you one wave, two wave, 0.5. So 0.6 here, as a 6.0 is 2.5 of your wavelength. Can you guys see that? That means, right, to find one wavelength, I take 6.0 divided by 2.5. So this gives you 2.4 meters. So divide by my wavelength 2.4, 3 divided by 2.4, I get 1.25 hertz as my frequency. Remember, I want to find period. So period is T. T is 1 over F. So 1 over 1.25. Okay. So I'll get 800 times, actually don't 800 times then 0.80 seconds. Now, I'm not done yet because the question is asking for W and not the period. So for this case here, W is 3 times the period. So 3T is 3 times 0.8. So this will give you 2.4. The C is the correct answer. Okay. All right. Good. Now, without any questions, let's move on to the next question, question 6. So far I've been talking a lot about transverse wave and the formulas and things to use if you are looking at transverse wave. Now let's take a look at next question here. which is a longitudinal wave. So sound, don't forget, sound is also tested under your wave properties. So for this question here, they straight away tell you that there is a longitudinal wave. Most likely you know it's sound because the only longitudinal wave that you have is sound waves, okay? It passes through a medium and the particles in the medium vibrates from side to side. So as you can see, right, for sound waves, the particle don't move up and down. So earlier on, Rakib, you said particles will go left and right. This applies only for sound wave. So as you can see, particle P here, it will only move to X, to Y, to X, to Y, like that. Okay? But because all the different particles, they move left to right at different time, it created an illusion that your wave moves from left to right. So now they say this particle here, or rather this entire diagram here, is shown when time is equals to 0. So now they say that particle P vibrates from X, then to Y, and then back to the position again, which is in the middle. Describe what happens to the distance between the adjacent particle when your wave moves through the medium. So basically, what they're asking you to do is describe for them how do all these particles actually come closer, move further apart? Do they do that when your waves travel? So if you recall, if it's a longitudinal wave, they form series of compression and rarefaction, correct? So compressions are regions whereby your particles comes closer together, pretty much like that. Or these are what we call your compressions. Rarefactions are regions where your particles are further apart from each other, which are like that. Okay? So even if you did not revise this part, right, the diagram themselves is already hinting to you how the particles distance between each other changes. So that's why we just got to say the particles distance between each other first decreases because they are at compression, then increases because they are at rarefaction, then they will return back to the original position. Okay? You cannot just mention, oh, it decrease then increase, full stop. You have to say that they go back to their original position because this question is asking you technically like an entire cycle, what happens. Okay, so I give you guys some time to write down your answers. Okay, the next question. Indicate on the diagram above two particles separated by a distance of one wavelength by labeling both with the letter R. Now, for transverse wave earlier on, we have seen that, right? The distance between two, it's not transverse wave, this is a graph, but let's just take this to be a transverse wave. The distance between two particles that were on the same point, okay, are taken to be one wavelength. So if it's this starting point, the next starting point, that will be one wavelength. The top here, this will be one wavelength. Bottom here, one wavelength. It could also be middle of the wave to middle of the wave, okay? But that's for transverse. For longitudinal wave, take note, the distance between one wave or one wavelength have to be from, there's two ways you can do this. One compression to compression or one rarefaction to one rarefaction, okay? So you go to your diagram, you find a compression as a compression or a rarefaction to rarefaction. Now, this is a compression, this is a compression. This is a rarefaction. So I can't do another rarefaction because there is no particles here. So I can only use this part and this part of the graph of the diagram. Okay. So like I said, it is between points that are on the same position. So if you choose R2, the center of the compression, as the starting point, then one wavelength later would be here, the center as well. Okay. So your answer can be R2 to R2. If you chose R1, the starting of the compression, then you can use the starting of the next compression, R1 and R1, or R3 and R3. So there are three possible answers here, R1, R2, or R3. Just write 1. Don't confuse yourself with or 3. But what I'm trying to show you is that wherever you choose to start, you have to end. Then that will give you the wavelength. Okay? Okay. Now, the next part here. The distance between X and Y is 8 mm. Now, read the question. They say distance between X and Y. So, if you go back to your diagram, let me just erase this. Between X and Y is this part here. And you realize, right, it is the distance that the particle oscillated. Okay? If I put this in a wave, do you all agree that, okay, let me just transfer this into a wave. Do you all agree that the particle that it oscillates, okay, is from here to here, then to here? So if I transfer this into my wave, this is how it looks like. That means your X and Y are the peaks of your amplitude. And if I tell you that the distance is 8 mm, what does this mean about the amplitude of the wave? It is 4 mm. Okay? So that's what that line is trying to tell you. Next, at time t equals to 2 seconds, all the particles in the diagram return to the original position for the first time. So read carefully. The diagram initially was at t equals to 0. T equals to 2 seconds later, they returned back to the original position. That means they are trying to tell you that this is 1 cycle. T equals to 2 is your period. Okay? So they gave you the wavelength as well to be 50 centimeter. Find the amplitude. Like I said earlier on, the amplitude is half of your 8, so it's 4 mm. That's why for this case here, 0.5 times 8 times 10 to the power negative 3. Oops, can you all write in a negative sign here? There should be a negative sign, negative 3. Okay. Then the next question, calculate the frequency of the wave. So you know your period here already is 2 seconds. To calculate frequency, you use the formula. Frequency is 1 over period. So you should get 0.5 hertz. And most likely the last one will require you to use V equals to F lambda because otherwise they wouldn't give you the wavelength, right? So calculate the speed of the wave. You know the formula V equals to F lambda. Okay. However, I want you guys to take note, all of these have to be in SI unit, meaning to say your V has to be in meters per second, your frequency has to be in hertz, okay? And your lambda needs to be in meters. So therefore, the screen is lagging a bit. Okay. So therefore, if let's say you were to have lambda in what? In 50 cm, make sure you convert them into meters. That's why I have 50 times 0.1. So my answer, 0.25 meters per second. Okay. All right. So that concludes my revision for waves. Hopefully you guys learned something and you are able to use that inside your WA1. Now, the next topic we're going to look at it would be for light. So if you can just turn your attention to the light chapter. Now, for light wise, just take note. At the end of the day, you will be tested on reflection, refraction, as well as lenses. So what you need to remember for them, all of them, right, is basically their formulas as well as how to draw ray diagrams, because those are essentially the two things that they do test you in light. Now, let's take a look at this part here first. Okay. For a lenses question, what you need to know is on top of the table that you need to remember, you would also need to actually look at whether the lens itself is converging or diverging lens. Okay. But for this first question, they stated here that you have a converging lens, right? Now, what I usually tend to remind my students is whenever you have a lens question, remember that you would need to draw a table or diagram, not say a table, that looks something like this. Remember in your textbook, you do have this table. I think I put it inside the notes. I didn't put it inside the notes, but what you have is this table that you need to remember of all the different scenarios in which where you place your object is along the lens, the image form will be what, all right? So for my students, I help them to actually derive a shorter summary for it so that you don't have to spend so much time memorizing the entire table. It's impossible to memorize. So this is the diagram that you always draw when you have a lens question. Your double arrow line here represents your lens, and then you just mark out roughly your focal point, two times your focal point, two times your focal point. Okay. So in that table, you have 6 positions of object that gives you different types of images. And that 6 position would be image object 1 here, object 2 at the focal point, object 3 in between the focal point and 2 times the focal point, object 4 at 2 times the focal point, object 5 beyond 2 times the focal point, and object 6 is slightly unique. It comes in as a parallel beam from a very far distance away. So of all these 6 different objects, where are the images? So I'll get them to draw. But before that, I will ask them to write. Images that are forming on the right-hand side are all real images. Images on the left-hand side are all virtual images. Okay? So then, where would figure 1 be? Figure 1 would be at this position here. So then you can see, based on the size of the arrow, the object, the image is virtual, magnified, upright, because the arrow is pointing up. Okay? Now, figure 2 would actually be somewhere around here. Technically, figure 2 don't exist, but I will just draw it here as because the image for figure 2, right, is upright. But it is considered to be real, upright, and magnified. Okay? But take note, figure 2 don't exist. It is technically at infinity. Then afterwards, my diagram starts to diminish in size, gets smaller and smaller. Figure 3 will be somewhere here. Figure 4 is your checkpoint. It is the only object and image that has the same size. And figure 4, if you realize, lies at 2F. The image will be at 2F as well. So figure 4 is sort of like the same checkpoint because figure 4 is exactly the same as your image and your object. And finally, figure 5 is somewhere here. So based on the size of the arrow, you can see the arrow size diminishes. So figure 5 is up. Sorry guys, I draw the wrong direction. I was misleaded by my tool. Figure 3 here. Okay. Figure 4 here, same size. Figure 5 here, diminished, inverted, and real. Okay. Figure 6 is the one where it can lie anywhere along this dotted line. So I don't draw an arrow for it because figure 6 can lie anywhere along this line. So this is the lens diagram that I will usually give my students to draw to remember if you have any type of lens question, just draw this diagram out. Okay, so let's take a look at the questions here. It says here, The diagram below shows a object when it's being viewed on a converging lens. The diagram shows path of two rays from the top of the object to the eye. Now, how does the image compare with the object? So for this question here, you take a look at your object, right? It is like that, correct? This size here. Now, if it's a converging lens, always remember your light rays converges until it meets the image. So the light rays need to combine until it meets the image. What you're going to do is, you're going to ask yourself, can the lens here combine? Then you realize the more you draw, the further they go. So what you need to do is, you will need to draw the light rays backwards. So extend the light rays as it is, and then for this part here, extend it as it is. So what do you realize? You realize your image is here. Okay. So what do you see about the image? The image is larger in size, is upright. Then we write the characteristics here. Magnified, upright. What else? On the back of the lens, so virtual. Okay. That's why for 1, you will have larger, upright, upright. So B is the answer. Okay, now the next question. Light is shown onto a transparent plastic block in air. Now, this is a very commonly tested question in a light question because, right, there is reflection and refraction at the same diagram. Okay, so you have light that enters at block X here. Block Y, most of the air is being most of the light, not most of the air. Okay, is being reflected, but some emerges along the air, along the surface of the block. Okay, so we don't look at the questions first. We don't look at what the question is trying to ask us first. We look at this diagram here. Number 1, your light ray is coming in at a specific angle. Remember, under refraction, always use the angle with respect to the normal, not the boundary. Yeah. So your normal is here. This is I. Your R will be here. You understand? So clearly from this diagram, you can see this is air into plastic. Therefore, this phenomena here is, I'm writing in blue, refraction. So under refraction, what is going on here? Remember, refraction, we always use FAST. Okay? So if I'm traveling faster, I will move away. If I'm traveling slower, I will move towards. So for this case here, if I'm moving from air to plastic, naturally I will travel slower because it's more dense. Therefore, I move towards the normal. That's why my angle is smaller. Then when I hit here, what happens? You can see that most of the light rays, or I think for this question, right, they stated that the light rays are reflected. So the angle here and angle here is the same. Means what is going on here? There is total internal reflection. Okay? Remember, when it's total internal reflection, what is the formula you use? You will have to use n equals to 1 over sine c, where c is what we call your critical angle. Which means to say, if you take a look at the diagram here, some of the light rays came out in this region, meaning to say that your light rays here indicated to you that the angle here, the I here, is the critical angle as well. That's why your refracted ray is 90 degrees. Okay? So these are what is going on here. There's refraction, there is total internal reflection, and then there is the refraction, but with critical angle given as this angle here. Okay, now let's take a look at now what the question wants. The question says, which diagram shows the angle of refraction at X? Oops. And the critical angle at Y, C at Y. So earlier on, we see angle of refraction is this one here, right? Then critical angle is this one here. So that's therefore your answer for this question would be C. Okay, so you realize, right, in the exam, please don't rush to go and answer your question. Just read through first, analyze the question first. Then you will, most of the time, right, figure out what the question is already asking you. The moment you analyze it, your answers will present itself naturally. Okay? Okay, now once you are done, let's take a look at C here, 3 here. The speed of light in a transparent medium is given to be 2.5 times 10 to the power of 8 meters per second. Which of the following correctly shows the ray of path through the right angle prism made of the same transparent medium? The keyword here, same, indicates to you that the refractive index N is the same. Okay, so same as what? Same as this question here. So first things first, let's understand how to calculate the refractive index. Under refraction, the next formula that you need to know to calculate refractive index would be N equals to C over V. C is the speed of light in air. V is the speed of light in the medium. So therefore, for this case here, the speed of light in air is a default at 3 times 10 to the power of 8. The one for the medium is 2.5 times 10 to the power of 8. Okay? So if you were to calculate the values, you will get a refractive index of 1.2. Okay, so for this wave here, the refractive index is 1.2. Now, they ask you, what happens to my light ray that now has an incident angle at 49? For this kind of scenario, you look at how your light ray is traveling from a more dense medium to a less dense medium. When your light ray undergoes more dense to less dense, travel from more dense to less dense, there is only two options it can go. Either refraction out of the prism or total internal refraction. So let's check whether total internal refraction happens or not. To do that, we will use critical angle. So remember, N equals to 1 over sine C. So C equals to sine inverse 1 over N. So earlier on, I calculated my critical angle, my refractive index to be 1.2. Therefore, my critical angle would be equivalent to 56.44, which is 56.4. Okay? So then you check, is your angle of incidence greater than your critical angle? Apparently not. Therefore, refraction happened. Total internal refraction will not happen. So you will not have A, neither will you have B, neither will you have C, because C is the critical angle. That means your I, right, needs to be equals to 56.4 exactly. A is if your I is equivalent to or is more than 56.4. Okay, same for B lah, but B less likely because it doesn't obey the rule of reflection. That's why your answer is D. All right. The next question, question 4. Now it shows here, the diagram below shows the position of a thin convex lens being used to produce real image. Remember, go back to our diagram here. Real image happens when what? When it is position 2, 3, 4, 5, 6. That means my object is placed at focal point onwards. Okay? So if we go to our question here, it stated that which position shows a possible position of the principal focus. Principal focus basically means your F, your focal point, correct? So how do I know which is a possible image for my principal focus? Remember, you need to have a real image, means position 2 onwards. And position 2 onwards means what? Means from the focal point F onwards. From F onwards, or you can say F and beyond. Okay? So is it possible for me to have it at B? Not possible, because B is most likely where your lens is. How do I know? Because B is the optical center. Okay? Remember, optical center is basically a light, the point where your light wave from the object cuts through the lens, one of the light waves. So B is obviously your optical center. So the options can only be A, C, and D. Now, obviously, your object cannot be placed, your focal point cannot be placed at C, because A object O needs to be behind the focal point. That's why A is the answer. Okay, the next question, question 5. A ray of light is incident on a horizontal plane mirror as shown. The light is reflected straight back the way it came. So basically what they're saying is that the light would came in like that, then went back up like that as well. The mirror is tilted through an angle of 10 degrees. What is now the angle between the incident ray and the reflected ray? So this is your light ray, alright? Originally 0 degree with respect to the ray. There is no angle between the normal as well as the light ray, because the normal is like that. Can you see that? So there is no angle in between. That's why incident angle 0, refracted angle 0. What happens when I tilt my mirror? Okay, maybe to make it less confusing, I'm going to draw the tilted mirror here. Okay, so that it's clearer. With respect to the horizontal, it tilted by 10 degrees. So what does this mean about my normal? Remember, your normal is always perpendicular to your mirror. So that means, right, your normal from the original position here was tilted by 10 degrees as well. So your light ray didn't change. Imagine your light ray is still down like that. Can you guys see that, right? The distance here and here is 10 degrees, because originally your normal was along the light. Then now it's tilted by 10 degrees. So this is how your diagram looks like. So if this is my incident ray, my refracted ray will therefore move up here by 10 degrees. Okay, so this is how my new diagram will look like. So what is the angle between the incident ray and the refracted ray? Between the two rays, it will be 20 degrees. Okay. Okay. Once you guys are done, let's now take a look at the next question. Now for the next question, I want to go through it together with you guys because it's a ray diagram drawing for lenses. Okay. Now, for this question here, remember, for a lens diagram, like I said, all your light rays will converge towards the image. Whether or not it comes out from the bottom or the top of the lens it will all meet at the image. But to determine the image, you simply just need two rays. So for this question, you have a converging lens of a camera to form an image that is IA prime of the object. F represents the principal focal. So they want you to draw image construction lines to find out where your image is. Now, how do we do that? Remember, for lenses, there is only two lines that helps you to determine the image, which is a line that diagonally cuts through the optical center. So that's the first line you draw. And the second line has to be parallel to the principal axis. This parallel ray has to cut through the focal point. Okay? Don't forget to draw your arrows as well. So what does this mean? This means that my image is at this position here, the point where the two light rays meet each other. I draw it downwards, then I label it IA prime. So then once I'm done with this, they say complete the path for AB, which is this ray here, and OC, which is this ray here, to locate the image IA. Remember what I say? For lenses, all the light rays converges towards the image. So therefore, for this case here, your AB just simply have to cut through here as well. This would be for part B. Your OC will also have to cut through here as well. This would be for part B. Understand? Then don't forget, draw your arrows. All right, the next question, they said, state what would happen to the image if the object is shifted slightly further away. So remember your object is now at beyond F, correct? Now, how do I then locate what happens to the image? So recall my diagram again. I said the diagram is very useful. It was at F. Beyond F means 3, 4, 5, 6, correct? So 3, 4, 5, 6, what do you realize about the size? The size has to become smaller. Okay? So you can see that it's becoming smaller and closer to the lens as well. That means the image is formed closer to the lens. So remember that diagram in the exam. If you can, just draw it very quickly. The image becomes smaller and nearer to the lens. Okay? So I give you guys some time to draw this. If you are still struggling, let me know. But just remember two things. Number one, two light rays help you to locate your image. The diagonal ray that cuts through the optical center, the parallel ray that cuts through the focal point. Then any other light rays that come out from the object will all cut through the object of the point of intersection, because that is one of the property of a converging lens. It converges into the image. All right. Now, once you are done, let's move on to the next question. Now, for this next question, it's sort of like a commonly tested application, because one of the application of total internal reflection, right, is that light is commonly used in optical fiber, which in this case here can be seen in cable television or, in surgical or medical industry. whereby the doctor want to find out, okay, if there's something wrong inside your intestine and they want to figure out what is wrong. Obviously, the doctor is not going to stuff his hand inside, right? That's a bit weird. And the hand is not going to travel all the way up into your, anus and rectum and whatnot, and then into the intestine. So what they need is number one, a visual image of the intestine. Number two, something small and light that can travel through. So what they use would be an optical fiber with a camera that is attached, let's say, at the front here, and then they will stuff that thing up into your hole, and then it travels into your small intestine or your large intestine. Then how do they take images? That's where light will be supplied into the optical fiber. So they need the light to travel through the fiber without losing much of the light and help you to take the image. And how do they do that? They will therefore make use of this property called total internal reflection. They make sure the light that they stand in is at an angle whereby the angle just nice is greater than the critical angle so that it keeps on like that. You understand? Okay, so for this question here, they say, if the optical fiber is mainly straight, light can travel at great distances without losing too much energy. But if it's bent too much, the light will escape. So they gave you the formulas for the optical fiber, whereby it's actually formulas that you have learned before, calculating your refractive index. But the refractive index that you receive in your school textbooks are usually very simplified because they assume that the other medium is air, the less dense medium is air. That's why the formula was n sine sine I over sine R, or sine R over sine I. But for this case here, the other medium is not air. If you realize the other medium is between a thick outer cladding or a dense glass center core. So the formula, the original formula was sine A over sine B equals to NB over NA, whereby B and A represents the different material. So usually what is B, what is A? The formula for B here would represent the more dense medium. It will always be the more dense medium over the less dense medium. Understand? So here they gave you the refractive index. Cladding 1.51, glass 1.69. Obviously, the glass is the more dense medium. The cladding is the less dense medium. Then they gave you the angle of refraction at X. So at X here, 52.7. You go to your diagram. Refraction, remember, with respect to the normal. So 52.7. Understand? Then angle of incidence at X, 45.2. So angle of incidence here, 45.2. So they say, given the equation and the following information, calculate the critical angle and the cladding boundary. So how do I calculate critical angle? If you look at the question here, critical angle means, right, your two uh, uh, medium refraction need to be present such that the light ray that comes out is at an angle of 90 degrees. Okay, so let me show you guys. The cladding is your NA. You all agree? The glass is your NB because NB more dense and A less dense. So theta A is the angle in your cladding. Theta B is your angle in your glass. So right here, theta A, theta B. Now, how do I calculate critical angle? My angle of refraction needs to be 90 degrees. That means the light ray comes out at an angle of 90 degrees, which is the angle at theta A, the cladding. So I'm going to sub in the refractive index 1.51, 1.69, but my theta A changed to 90 degrees so that my theta B is the angle here, my critical angle. That's why sine 90 over sine C equals to 1.69 over 1.51. And that's how you get your critical angle, 63.3. Okay? All right. Then the next question. Hence, explain why the change in direction at point X cannot occur at point Y. So what's the difference between point X and point Y? If you take a look at point X here, the angle here is 45.2. Remember, earlier on, we have already found out critical angle is 63.3 degrees. So at X, what do you realize? Angle of incidence is 45.2. It is smaller than your critical angle. So what happens? Only refraction. Okay? But at Y, take a look at Y. The critical angle is, the incident angle is 69. It is greater than the critical angle. Therefore, total internal reflection happens. Okay? So basically, the question is asking you to explain why total internal reflection can happen at Y and not at X. And it is a classic question that they always like to ask in the exam to explain total internal reflection. So remember, in the exam, if you want to explain total internal reflection, you need to write down these two things. Number one, your object moves from less dense to more dense to less dense. You need to literally write down the light ray moves from optically more dense medium to less dense medium. Number two, you need to write down that the angle of incidence was greater than the critical angle. Therefore, total internal reflection occurs. Okay? So that's how you will phrase your answer. Knowing that what the question wants, those two, you say, light travels from optically denser glass to optically less dense cladding at both A and Y. X and Y, sorry. There shouldn't be an A. Okay. Then at Y, the angle of incidence for 69 is larger than the critical angle, but at X, the angle of incidence is smaller than the critical angle. Hence, then you state the process. Refraction takes place at X, but total internal refraction takes place at Y. Okay. The annotated worksheet, I can drop it into the student drive. So I believe you guys actually received an email with regards to where you can obtain the online worksheet previously. So let me drop the annotated worksheet into that drive as well, and then you retrieve from it. Because I don't know, I don't have any of your contacts, so I can't email to you guys. So the only way I can do it is through the online drive. Okay, clear? All right, good. So hopefully today you guys are able to understand light and wave better so that your WA you are more prepared. But like I said, physics is not something that you can just memorize the content and then go for the exam. And it's basically like math. You have to really do a lot of practice. So for a start, for those of you guys who don't know what questions to do, other than my regular students, your homework, the on other online students who are not my students, can you guys at least try the TYS topical? Okay, your topical has good enough kind of integrated questions to help you prepare for the WA. Maybe you want the link to the drive. Yeah, wait, let me see if I have the link to the drives because yeah. Okay. I just sent the link to the Google Drive for the student access for the worksheet. Later I will be dropping in the annotated file so that you guys can retrieve it from there. Okay? Okay. So let me just do a proper closing for you guys. Now that you all have went through it, if you are interested in joining our regular class, because right, currently what I went through here is probably maybe about 50% of what we do in regular class. Obviously, regular class, we do have more content, we do have more concepts, we do have harder concepts as well that we tackle. So if you're interested, you can actually scan the QR code. All of you guys are Sec 4, you can look at this sites here. Just scan the QR code. The timetable is too small already. I do have classes mainly at Tampines and Kovan. So if you're nearby there and you do want to join us, join early because I can't help you if you only join in, let's say, September or October. That's worse. Okay. So at least join early and hop onto this bandwagon with us early. Can? Okay. So just scan the QR code if you do want to have access to your the time slots if you can. And if you are happy with today's session, you can actually scan this QR code and do a review for me lah. Can? Okay. And if you don't have any other questions, you can drop off the call.